So I'm going to start by looking at these problems, the homework problems that you tried. Do you have those with you so you can follow along?
Yes.
Okay, let me take a look. Okay, that looks like a right answer for number 1. It's correct for number 2. It's correct for number 3. Correct for number 4. Number 5 is correct. Okay, that's correct for number 6. Number 7 is correct. Okay, let's turn on your screen.
Can you see my screen?
Yeah, thanks. Okay, so let's see. So let's start by writing down, say, the logarithm of p is q. The logarithm of p equals q. Let's start by writing that down. Good. And now let's rewrite that as an equivalent equation that doesn't have the log in it. Okay, very good. So do you remember, what do we call the 10? What's the name for what the 10 stands for?
The base?
That's right. How did you know the base was 10? How did you know the base was 10? I don't see any 10s there.
It's assumed.
That's right. If it was written, where would it be written? Right in the base in the position it would be written in the original equation if it was there. Yeah, it's written, that's what's called a subscript, right? So the base is written as the subscript of the logarithm, but if it's not written, you assume the base is 10. Okay, now let's, you have the homework in front of you? Let's try question 8, part B. We want to do part B from question 8. You can tell me when you think you have an answer.
I have the answer.
Okay, what's the answer?
2.
Okay, that looks like that's correct. How did you know the base was 10?
Because it's assumed.
Yeah, there's nothing written there in the subscript. Good.
I did the same mistake for all of them, actually.
Okay, so I'll take a look at here at number at B here. So take a look at the work that you did here for B. Can you see what went wrong and what you wrote down here?
Yeah, I accidentally wrote 100 as the base.
Yeah. Okay. And so when you did that, you ended up with an incorrect answer. So what should you have written over here?
100 to the y power.
That is what you wrote.
I'm sorry. What 10 to the y power is equal to 100 and y is equal to 2?
Yeah, not equal to 1. I'm not sure where the 1 came from. Okay, so that one was mistaken. So I'll take a look at C. I think maybe you said this one came out incorrect as well. So how should you have written this one out?
10 to the y is equal to 10, so y is equal to 1.
So what's the answer to C?
1.
Okay, so we got a little confused on those two problems. And let's try D. How would you do D?
10 to the y is equal to 1, and y is equal to 0.
All right, so it looks like we got a bunch of these incorrect. So logarithms are going to come up in the course. Most logs you can use a calculator, but it's important to have just a little basic intuition for how they work so we can avoid mistakes and have some understanding. So B, C, and D, it looks like we were getting confused on those. And how would you work out E?
E is 10 to the power of y is equal to 0, so y is equal to 0.
Did you write that out on paper? Try writing that out on paper.
I just assumed since there was a 0 that everything would be 0. So I would show you. Do you want me to share my screen?
Okay. Okay. So you said the log of 0 is 0?
Yes.
Now let's check that. Why did you say y was 0 here?
Because 10 to the 0th power is 0.
Is that true? What is 10 to the 0th power?
One.
That's right. Do you remember a couple of sessions ago we kind of had a little digression where I tried to explain why anything to the 0th power is 1. So, yeah, so what is 10 to the 0th power?
1.
Yeah. So is y equal to 0 on this problem?
No.
That's a mistake. Actually, if you think about it, since 10 is positive, there's no way to multiply 10 by 10 and get a 0. So what we've actually seen here is that this is undefined. You could also check this on your calculator. If you try to do log of 0 on your calculator, it'll give you an error to show that it's undefined. So this is undefined because if you start with a positive number, you can't multiply a positive number by itself and end up with a 0. So what this shows us is we can't take the logarithm of 0. We can't just assume because there's a 0, the answer is 0. That's something we talked about in our previous session. Okay. So it looks like we were getting E wrong as well. So let's try F. You said F was undefined. How would you prove that F is undefined?
You can't take the log of a negative number.
But let's make sure we understand why that is. What would happen if you tried to take the log? How can you see that that's undefined?
It's undefined because you can't multiply a positive number. Oh.
So try writing it out the same way as we've been writing out these previous problems.
10 to any power cannot equal 4, -4.
Can't be negative. Okay, so that confirms that that one is undefined as well. So like I said, you'll be working with logs in the course. Usually you'll use a calculator, but it's important to have some basic feel for how logarithms work, and that's something we spent some time on before. Okay. All right. So for number 10, looks like we didn't quite get this correct. We didn't write down the chemical equation. This equation that you wrote down, 10 to the negative 7 times 10 to the negative 7 equals 10 to the negative 14, this is just a special case. This is the case of pure water. They're not always equal to 10 to the negative 7, so the general equation is the one that you wrote down here. Okay, so this is a correct answer for number 11. Let's see, number 12, part A is incorrect because you left out the units. We always have to include units. What should be the units here for part A? Okay, that's important. In science, we have to include units. That's not a minor detail. That's crucial. So that's important, but the number here is correct. And what were the units for part B? So I was asking you, so again, part B here is incorrect because we left out the units. What should be the units for part B? Okay, that's important. But otherwise, the numerical solution here is correct. So here you used the mathematical equation for water autoionization. Now look at part C. Part B you said was acidic. That's true. Okay, and again, what should be the units for part C?
Mole.
Okay. And was part C acidic or basic?
Part C is basic.
Okay. Okay, so this is correct for number 13. pH doesn't have any units, so that's correct.
So how much more acidic would something like part C be compared to something that's 4 times 10 to the negative 9? That'd be 20 times more acidic.
You were comparing these?
Yeah.
Okay, that's a good question. That comes up a lot, so that's an important question. Well, let me ask you this. Do you know how to simplify this without a calculator? All right, so you asked a good question. That's actually an important question, so let's look at this. Do you know how to simplify this mathematical expression without using a calculator?
8 to the power 4.
How did you figure that out?
If you divide numbers with the same base and different exponents, so just subtract.
You subtract the exponents. That's right. Good. So what would this be?
1 over 11 to the power of 5.
That's true. If you just use the subtraction technique, you would get this. But these are the same thing. So the way you did it is maybe better. The answer you gave was a good one. Good. So in general, how do we simplify this expression?
X to the power of y minus z.
Or, as you already explained, it could be 1 over x to the z minus w. Good. All right, so you were asking me which of these was more acidic. So
how many times?
How many times more acidic? Well, when you're asking how many times more, you're trying to set up a ratio. So you just need to put these in a ratio. Now, the ratio will be easier to interpret if we put the bigger number on top. Which of these is the bigger number?
The bigger number is 10 to 4 times 10 to negative 9.
So what you were asking me was, what's this ratio? Will you tell me, how would you go about simplifying this ratio? You might have to work that out on paper a little bit.
One over 4 times 10 to the negative 20.
Can you repeat that?
1 over 4 times 10 to the negative 20.
All right, doesn't sound like that's coming out correctly. First of all, the 4's just cancel. If you see what I'm saying?
Yeah.
So there shouldn't be any 4's in your answer.
Okay.
Then what?
1 over 10 to the negative 20.
I'm not sure where you're getting that negative 20.
Is it negative 9 to minus negative 11?
Okay, what do you get when you do that calculation, negative 9 minus negative 11?
Oh, it's 10 to the second.
Not 20, huh? So we have to be careful with the negative signs. Okay, so let's try one more time. What answer are you getting?
10 to the second. 1 over 10 to the second.
Now, why are you saying 1 over?
Because it's negative 9 minus negative 11.
That's true. What is negative 9 minus negative 11?
2.
Positive 2. I'm still not quite sure why you're putting this on the bottom.
Okay,
So over here, when you did the 1 over business, you did the 1 over because 3 minus 8 would have been negative 5, and you didn't want to deal with a negative exponent. The reason you did 1 over was to avoid having to use a negative exponent. But if you subtract negative 9 minus negative 11, that doesn't give you a negative exponent. So the answer here is really 10 squared. And what is 10 squared?
10 squared is 100.
So how much more times acidic is this one than this one?
100 times more acidic.
Okay. I think before you might have been guessing maybe 20. So that's an important question. That's something that might be tested or come up. So that's a good thing to have asked. Let's practice that a little bit more. So if we have, say, 10 to the negative 4 versus 10 to the negative 5 molar, how much more acidic is the first one than the second one? How would you work that out?
Divide, so 10. We're going to 4, 10, negative the negative 5. Get 10.
So negative 4 minus negative 5 is 10 to the first, which is 10. So this is 10 times more acidic. That's right. Okay. Why did we put the 10 to the negative 4 on the top instead of the 10 to the negative 5th?
Because it's a bigger number.
Yeah, it's just going to be easier to work with if we put the bigger number on top. So you can make your life easier by putting the bigger number on top.
So it's like one unit away from another number. Like the negative 5 is negative 6, 10 times different than each other. And
yes.
And negative 5 and negative 7 are 700 times. So each interval, as it goes up,
Yes,
Okay.
that is correct. So that's actually pretty important. Good. So let's just reinforce that, but it sounds like you were summarizing that correctly. So how would you compare these?
That'd be 100 times more acidic.
Good, but let's make sure we understand the method. What's the method for comparing them?
So you would put 10 to the negative 5 over 10 to the negative 7. You would get 10 squared.
And that's 100. Okay. So then suppose you were comparing, say, let's say you were comparing these. Well, what number would you put on top?
The bases are not the same.
I think you mean the coefficients. The coefficients are not, that's true. But in any case, what number would you put on top of the ratio if you were trying to compare them?
4.5 times 10 to the 30.
Because you want to put the bigger number on top. Now, if you want to know the exact comparison, you can just use your calculator. So all we need to go over is how to approximate this. Well, what's more important in the value of these numbers? What determines the value? What has a bigger impact on the value? The coefficient or the exponent?
Exponent.
Far more important. So if you're going to approximate this, you can just approximate it as 10 to the negative 3 over 10 to the negative 6. If you need an exact answer, you can just pull over your calculator and do the calculation. So all we need to do is just see how we can kind of eyeball this. So how much more acidic is the right hand than the left hand?
The right hand is 1,000 times more acidic.
That's right. Okay, so that's kind of the answer to your question. So first of all, the first part of my answer is if you want to know how many times more one thing is than another, what you might not have realized is you have to set up a ratio. So the way you do these is by setting up a ratio. And then if you wanted, you could just stop and use your calculator. Once you've set up the ratio, you could just use your calculator to get the answer. However, your instructor probably expects you to be able to kind of have a feel for these a little bit. The way to have a feel is to ignore the coefficients and just focus on the powers of 10. Just focus on the powers of 10 to just get a feel for the order of magnitude difference between them. And then we just use the idea of subtracting the exponents. Does that answer your question?
Yes.
Okay, so that's important. Okay. So let's see. I was looking at number 14.
Are those your kids?
Nope, just neighbor kids.
Oh.
It's hot, so I got my window open. I'm sure they're not having as much fun as we are. Okay, that looks like a good approach for number 14. Okay, so you saw what I was going at here for number 15. This is the general chemical equation for acid ionization. The right-hand side isn't quite written correctly. What's missing on the right-hand side of that chemical equation? You should just be familiar with what chemical equations look like from your chemistry courses. So what I'm going at is there has to be a plus.
Oh.
This plus A minus is the chemical equation. It looks like you left that out down here as well. So chemical equations, we don't just write the species, we write pluses. That's the way they're written. All right, but otherwise that's what I was going for number 15. Let's look at number 16. All right, this is the right answer for number 16. You kind of didn't quite finish the table here. You wrote down the signs on the changes, but you didn't write down the numbers. So refresh your memory here for number 16. So you said that HBr concentration is going to fall. That's why you wrote a negative here. But how much is it going to fall? The change will be negative what?
Negative 0.0023.
And then what would be the change in the H plus?
Positive 0.0023.
And how about the Br minus?
Positive 0.0023.
Okay, so in order to use these tables consistently, it's important to fill in those numbers there in the middle as well. But you got the right answer there for number 16. All right, this is good for 17. How do you know that this will have a negative sign?
Because it lost the hydrogen.
What was the sign on the hydrogen?
Neutral.
Well, if it lost something neutral, it would stay neutral, wouldn't it?
The sign of the hydrogen. Wait. 17. It lost a proton.
What's the sign on the proton?
Positive.
So that's how you know it's negative, is my point. If you start neutral and you lose something positive, you become negative. So it's better not to say we're losing a hydrogen. Instead, we should say we're losing a proton, or an H+, because the sign is very important. Remember when we were talking about organic chemistry? For your organic chemistry course, we kept emphasizing how important charges are. So the charges are important here as well. All right, but this was the right answer for A. So how did you know that the answer was negative for B?
Because we lost proton.
And what charge did it start with before it lost the proton?
Neutral.
Okay, so that was correct for B. C was a little bit tricky, but it looks like you got that correct as well, so that's good. How do you know that it ended up positive?
Sorry.
How do you know that C ended up positive?
Because when you want to write, you have to add a proton.
And it started neutral, so it ended up positive. Okay, that was right. This looks correct for D. All right, and that looks correct for E. All right. 18 is correct. 19 is correct. 20 is correct. 21 is good. All right, that's good for number 22. Okay, this is a tricky type of question. This is important, and you remembered the correct way to do it, and you put some units on your answer too, so that was good. That was a good use of symbols for proton concentration, so that's right for number 23. Okay, I think those are important questions, so it's good that you took the time to work through all of those problems. Some of them you missed, so hopefully you marked those. Okay, so continuing on. So one of the problems that was in the homework was, let's see, number 16. Yep, looking at number 16. Do you remember that on acid-base problems, there's many different types of acid-base problems. You might start with a strong acid or a weak acid, a strong base or a weak base. You might have a combination of acids and bases. So what type of question was number 16? What type, were we starting with an acid or base for number 16?
Number 16, we which one for the homework?
Yes, please.
That's an acid.
Good. And is it strong or weak?
Strong acid.
Okay. So you have down how to do those types of problems with strong acids. So let's take a look, say, at this. So here's a problem. Now, what type of situation... Do you have that acid-base handout that I sent you previously?
Yes.
Okay, so that summarizes all the different types of acid-base problems. As we've seen, there's lots of different types. So which type is this? What have you been given in this problem? An acid or a base or a combination? Actually, I'm sorry. I didn't write the problem correctly. Let me write it like this. Here's the way I meant to write the problem. So in this problem, have you been given an acid or a base or a combination?
Base.
Strong or weak?
Strong.
Okay, so we haven't learned how to do that type of problem yet. There's an example of this that your instructor did in the lecture, though, so let's make sure we know how to do this. Let me show you how to deal with this. Now, the equation for a strong base is not the same as for a strong acid. So the equation here for this base looks like this. If this was going to split, what pieces do you think it would split into?
Sodium and hydroxide.
What's the charge on the sodium?
Positive.
And on the hydroxide?
Negative.
Okay, good. That's the definition of hydroxide. So notice this is not the same type of equation that you used for strong acids. The problems with strong bases are solved differently than strong acids. Here's the equation for a strong base. Now again, we should have a before, during, and after table. The first row is the concentrations before the reaction happens. Then here we write down the changes during the reaction. And then we write down the concentrations after the reaction. So what number do you think goes here before the reaction has occurred? So the question I was asking you is, what number do you think goes here before the reaction has occurred?
0.0054.
That's good that you included the units. Before the reaction has occurred, what's the concentration of this product?
0 molar.
And how about this one?
0 molar.
Now, during the reaction, is this concentration going to increase or decrease?
This is going to decrease.
So is this a plus or a minus change?
Minus.
Minus what?
0.0054 molar.
How do you know that all of it is going to react?
Because it's absolutely strong.
Yeah, it's a strong base. How do you know it's a strong base? Well, first of all, you have it memorized. Also, if it wasn't strong, they would have to give you what's called the Ka, or the Kb for the reaction. So does this reaction go to completion or to equilibrium?
Completion.
Yeah, reactions with strong acids and strong bases go to completion. Reactions with weak acids and weak bases go to equilibrium. So then what's the change in the Na+?
Hold on, sorry, I was writing that down.
Take your time. That's actually an important point. So reactions for strong acids and strong bases go to completion. Reactions for weak acids and weak bases go to equilibrium. That's the basic difference between them. That's kind of the definition of strong and weak.
Okay.
What goes here?
Positive 0.0054 molar.
And what number goes here?
Positive 0.0054 molar.
And how about here?
0 molar.
And here?
0.0054 molar.
And here?
0.0054 molar.
Good. Notice we only put pluses and minuses on the change row. The before is always positive, so there's no point putting the positive signs. And after is always positive, so there's no point putting the positive signs. But changes can be positive or negative. Now remember, what was the question?
What is the pH?
That's right. Now, how are we going to find the pH? This is a little bit trickier than when we have a strong acid. Do you remember what's the definition of pH?
It's the negative log base, or the negative log of the concentration of protons.
Now, do you see why this is going to be a little bit trickier? Because this equation doesn't tell us about protons exactly. This doesn't have protons in it. But what information can we get now from this? So the row we're going to use is the after row. So which number here in the after row can we use to try to figure out the pH?
0.0054 molar.
But what does that represent? That's equal to what?
The concentration of hydroxide ions.
That's right. Notice it's not the concentration of protons. So now what?
Now we can get the pOH.
How would you do that?
pOH is equal to the negative log of the concentration of hydroxide ions. So it's negative log of 0.0054.
That's good so far. So keep going ahead and solve the problem and tell me what you're getting.
.267 is the pOH. So I would have...
Be a little bit more careful in how you rounded that. What should this digit be?
it doesn't show me. I'm using my phone calculator.
Oh, okay. All right. It's better for the tutoring sessions to have the same calculator you're going to use on the test. But in any case, okay. So if we round it off, it would be 2.68. Okay. So now what?
You would have pH plus negative 2.268 is equal to 14.
Like this?
Hold on a second. Yeah.
Okay. Now, one thing that's always good, it's always best to write the general equation before you start plugging in numbers. So before we plug in the 2.268, what's the general equation that you're plugging into here?
pH plus pOH.
And here we can write a number. What number goes on the right?
I have pH plus pOH is equal to 14.
Good. Okay. So what we're going to plug in here is the pOH. What is the pOH? What is the pOH?
pOH is negative 2.268.
Why did you say it was negative?
Oh, sorry, it's 2.268.
Yeah. So I think you got confused. The pOH is the negative log. The pOH is the negative log. But the negative log here turned out to be a positive number. So it looks like we were starting to make a mistake there. So to review, what is the pOH? What number is it here?
The pOH is going to be 2.268.
Positive. So here this should be a positive number. Okay, so now what?
So we subtract 2.268 from 14.
Okay, and what do we get?
11.732
And what does that number represent?
pH.
So what do we do now?
We put 11.732 molar.
So what's the answer to the question?
pH is 11.732
What are the units?
molar.
Okay, that's not quite right. pH doesn't have units.
Oh.
So we would lose some credit for that. Okay, so what's the answer?
11.732.
Okay. All right. So this is a new type of problem that your instructor did an example like this in the lecture notes he sent me. So it looks like this is something that could be on the test. This was in the review problems too. So here's how to do this type of problem. So remember, you have that acid-base handout with you. Which type of problem is this from the acid-base handout? What type of starting material did we start with here?
Which acid-base handout?
I've only sent you one. I've sent you one acid-base handout. So that handout shows that there's many different types of acid-base problems. So which of these types did we just do?
Strong base.
Okay. This is the first time we ever did a strong base problem. Do you see this is kind of different from the strong acid problem that we learned how to do before? How is this different? The main difference is that the chemical equation is different. Notice that this chemical equation is different for a strong base. The most important difference is that we're not making protons, we're making hydroxides. This was a little bit harder because we were making hydroxides, not protons. A lot of people here get sloppy and they think that the answer is 2.268 because they don't realize this is the POH and not the pH. So here's where it is important to make the table very carefully to see that you're doing this correctly. So I would recommend when you're doing these problems, write out the chemical equation and write out the before change after table carefully. Now I saw that in your lecture notes, your instructor wasn't writing down all these steps, but that's just because they're doing these in their head. So a beginner has to write down all of these steps, even if your instructor is skipping them. We can't do this in our head. So this is how we do a strong base problem. Hopefully that made some sense. And the important thing is not to confuse it with a strong acid type problem. Also remember, we've seen there are two levels that we're working with. There's the concentration level and there's the P level. We don't want to confuse the concentration level and the P level. For example, notice this answer is at the P level, so it's not in molar. Molar is units that are used for the concentration level. The concentration level has units that are molars, but the P level has no units. We don't want to confuse those two levels. Did our answer come out to be acidic or basic? pH. Hi, did you hear that question? My question was, did the answer come out to be an acidic or basic pH?
Basic pH.
That's right. Why should we have expected that from the start?
Because we're using a base.
Yeah, we added even a weak base would give us a basic solution. And here we're adding a strong base. All right. Okay, so try doing this problem on your screen. Let's try this on your screen. Try to use the systematic techniques we've been talking about. Before we use your calculator, let's try to make a prediction. What would you predict about the pH of this solution? What would you predict about the pH of the solution?
It's going to be a basic. So it's going to be about 10 to the negative 7. It's going to be smaller than 10 to the negative 7.
Careful, I think you're confusing those levels. You're confusing the concentration level and the P level.
Oh, it's going to be a number that is higher than 7.
Yeah, do you see what I mean by confusing the levels? At the P level, we don't use the 10. Okay, so let's continue then with our calculations.
pH is equal to 7.568.
Does that match your prediction?
Yes.
Okay, good. All right, that was a good systematic approach. I just wanted to mention, I noticed that I gave you that the concentration was 3.7 times 10 to the negative 4. I gave you the concentration in scientific notation, and you chose to write that as an ordinary number, 0.00037. And that's fine. That's totally fine. I just wanted to point out you don't have to do that. If you wanted to, you could have just left it in scientific notation in your table. So the way you did it is fine. If you prefer to write it as a decimal, that's fine. But you should keep in mind you could just do the table in scientific notation as well. But the way you did it is just fine. Okay, so that's a good method for that problem. Okay, so again, to review, what type of problem from the handout have we just learned how to do?
A strong base.
Strong base, yes. And if you recall, in our last session, we went over how to do strong acid problems. There was an example like that in the homework that you did correctly. And we also went over how to do pure water. Remember, what's the pH in pure water?
7.
Yeah, 7. Okay. And we also showed how you could prove that using the KW. Or you could just have it memorized. Okay, good. All right, tell me when you have this problem written down.
Okay.
Okay, so now what type of problem is this? Which of this categories in the handout would this fall into?
Is it a weak acid?
That's right. How do you know it's an acid? Well, they gave you the Ka. Do you know what type of functional group this is?
Carboxylic acid.
Right. In fact, this is acetic acid, which is a common acid in the course. How do we know this is a weak acid? Well, first of all, it wasn't in the list of strong acids that we memorized. But also, remember, if they give you the Ka, that means it's a weak acid. If they give you the Ka, that means it's a weak acid, because the Ka, remember, is an equilibrium constant. But only weak acids have equilibriums. So this is a new type of problem that you and I haven't gone over yet. But again, there was an example of this in lecture and in the practice problems. So we should see how to do this. All right, so this is going to be a slightly new method. Again, each problem, unfortunately, is slightly different. So this is a weak acid type problem. Each type of problem from the handout is slightly different. First of all, we have to write the acid ionization equation. That's actually going to be pretty similar to what we've seen before. What do you think I should write on the left-hand side for this acid ionization equation?
CH3COOH.
And it's best to show that that's an aqueous. So we're writing the chemical equation. And then what goes on the right-hand side, do you think?
COOH, or CH3 plus COOH.
Like this?
Plus COOH.
Okay, I'm sorry, could you repeat that again?
CH3 plus COOH.
All right. Well, remember, what is this? Is it an acid or a base?
It's it's an acid.
What do acids do? What's the definition of an acid?
It donates protons.
They don't donate COOH groups. So we can tell what these should be by remembering this is going to act like an acid. So did you have any second thoughts? What could we write on the right-hand side?
CH3COO minus plus H plus, or plus H plus.
Okay, that's much better. And again, it's best to show that these are an aqueous solution. Okay, we should be able to figure that out because we know this is an acid. Acids donate protons. That's what they do. Okay, and again, we'll do a before, change, and after. Maybe before we continue, we should have made a prediction here. What could we have predicted about the pH before we did any math on this problem?
That it's going to be below 7.
Because we have an acid. Even a weak acid will give us an acidic pH. So we predict the pH will be below 7. Okay, what do you think we should write here?
.7 times 10 to the negative 3.
That's right. Molar. And how about here? What goes here?
0 molar, 0 molar.
Why are these 0? Because before the reaction has occurred, there's no products yet. All right, now, will this change be positive or negative?
That change will be negative.
Now, we have to stop and think about this for a second. Is this reaction going to completion or to equilibrium?
That is going to equilibrium.
How do we know it's going to equilibrium? Because it's a weak acid. They gave us a hint because they gave us the equilibrium constant. So are we going to use up all 3.7 times 10 to the negative 3 molar of starting material?
No, we're not going to use it all up.
No. How much are we going to use up? Well, we don't know. We don't know how much we're going to use up. If you don't know how much a number is, you have to use a variable for it. So here's where this starts to be different than the strong acid problem. For a strong acid, we would know what this number is. For a strong acid, we would just use up all the acid. But weak acid problems are different. We don't know how much of the weak acid is going to react. So for a weak acid, you have to write down a variable. So we've said we're going to use up X molar of this. Does that make any sense so far?
Yes.
Now that I've shown you how to write this, what do you think we would write here?
Plus X.
That's right. However much we use up, that's how much of this conjugate base we're going to produce. And what goes here?
Plus X.
Good. So then what goes here?
X.
I think you're not understanding the table. Remember, this is a before change after table. How would we figure out what goes here?
0 molar.
No, we're not understanding. How much did we start with?
3.7 times 10 to the negative third.
And how much was used up?
Negative X.
Yeah, X was used up. So how much would be left over at the end?
So it's just 3.7 times 10 to the negative third minus X.
That's right. Do you see how the table is supposed to make that obvious? Before, change, after. You start with the before. This tells you how to change it, and then you get the after. Do you see it doesn't make any sense to say this would be X? That's a misunderstanding how the table works. Here's how much we started with. Here's how much it decreased by, so here's how much we end up with. Okay, do you see how that's consistent with what we did before? For example, here, how did we get the 0? Well, 0.0054 minus 0.0054 is 0. We're supposed to be able to figure out what the after is. Okay, so then what number would go here? Or what would I write here?
Plus X.
How did you calculate that?
0 plus X is X.
That's right. That's all there is to it. Once you understand it, the table is supposed to be really, really simple. You start with the before, then you make the change, and then you have the after. So before plus this change gives us the after. We don't put a plus sign here because this is always plus. You can't have a negative amount left over. And then what would go here?
X.
And how did you calculate that?
Because 0 plus X is X.
Yeah, it's just that simple. But it's important to understand while we're writing these things down rather than just doing it mechanically. Okay, so it looks like we're not in as good shape as we might have been for a strong acid problem because we have all these X's running around. We're going to need to write down a mathematical equation so that we can solve for X. We need some mathematical equation that we can solve for X. So what we need to do now is write the mathematical equation for acid ionization. The mathematical equation for acid ionization. We briefly talked about this in our last session. What you do is you put the concentrations of the products on the top. This is something that you learned how to do in general chemistry, but you might have forgotten. You put the products on the top. You put the starting material on the bottom. If there was anything here that was a pure liquid, we would leave it out, but these are all aqueous, so they get included. And on the right-hand side, we write the equilibrium constant. So this is the mathematical equation for acid ionization. Here's the chemical equation for acid ionization, and here's the mathematical equation for acid ionization. We put the products on the top and the starting material on the bottom. Tell me when you have that down.
Okay.
Okay. Now we have to start plugging in using our table. We're going to use the after row for the table to plug in. We want to know, because the after row shows us what things look like in equilibrium. So according to the table, what's going to be the CH3COO minus concentration in equilibrium?
X.
That's right. You got that from here. And what's going to be the H plus concentration in equilibrium?
X.
You got that from here. And what's going to be the CH3COOH concentration in equilibrium?
3.7 times 10 to the negative third minus X.
And what do I write down on the right-hand side?
Equals 1.74 times 10 to the negative fifth.
Good. So that's good that you remembered that we know that number. They were given the equilibrium constant in the problem. So you can see where the table is important. The table tells us what to plug in to this equation. We use the after row here to plug in. Okay. Now, we should be a little worried because this looks like a pretty complicated equation. This might be a little bit tough algebra to solve. We need the quadratic formula to solve this. Your instructor doesn't actually expect you to use the quadratic formula here. What we're going to do instead is, usually for these weak acid problems, only a small fraction will be reacting. Usually only a small fraction of the weak acids will be donating their protons. Usually only a small fraction of the weak acids donate their protons. Does that mean that X is usually pretty big or small?
Hello?
Yes, I'm here. I guess we cut off. I was saying that usually with a weak acid, only a small fraction of the weak acid will donate their protons. Weak acids usually only donate a small fraction of their protons. So in that case, would X here be big or small?
X would be small.
Because we said only a small fraction is going to be reacting. So would you agree? That means that 3.7 times 10 to the 3 minus X is going to be approximately 3.7 times 10 to the 3 minus X. That is, if you subtract a much smaller number from a bigger number, the number doesn't change very much. Oops, this should be in minus 3. If we subtract a much smaller number from a bigger number, the number doesn't change very much. Does it make any sense?
I'm sorry.
Yeah. Are you there? Are we cutting off? Sometimes there's a long pause. Maybe you're not hearing what I'm saying. Is there?
Yeah.
Is the connection cutting out?
Yes.
No. All right. That's too bad. All right. Well, he'll keep trying. What I was just trying to explain that since X is much smaller, so for example, what is, let's say, suppose you have $1 million. If you have $1 million and then you lose $2, how much money do you have left? If you have $1 million and someone takes away $2, would you agree that you still have approximately $1 million left?
Yes.
Who cares about the $2, right? This number is so much smaller than the 1 million, it's negligible. So if you were a millionaire and you spent $2 in a candy bar, you would hardly even notice it. You would still say, I still have about $1 million. So it's the same deal with these weak acids, such as only a small fraction is going to react. So how much of this weak acid did we start with? How much of the weak acid did we start with?
3.7 times 10 to the negative third molar.
And only a small fraction of it is going to react. So about how much of the weak acid will we have in equilibrium?
Approximately 3.7 times 10 to the negative third molar.
Yeah, that's right. It's just like if Bill Gates has to spend $2, it has almost no effect on his wealth. If such a small fraction of the acid is reacting that there's going to be has almost no effect. So we're going to make an approximation here. Instead of writing 3.7 times 10 to the negative 3 minus X on the bottom, I'm just going to write 3.7 times 10 to the negative 3. This is the same technique that your instructor used in the lecture notes, but I'm just trying to explain where this comes from. So, so that's a trick that you're always going to use on weak acid problems in this course. Your instructor, if you don't use this trick, you would have to use the quadratic formula. But I don't think your instructor expects you to ever use the quadratic formula. So whenever you have these subtractions in the denominator, you should always approximate it by just treating the X as negligible. All right, does that make any sense? Do you see where I got this equation from now?
Yes.
So now what?
Now solve for X.
How would you do that? What should I write down next?
Multiply 3.7 times 10 to the negative third on both sides.
Good. So what's the new equation?
So X squared is equal to
X squared is equal to 6.438 times 10 to the negative 8th.
Good. Now what?
Square root both sides.
Okay, so let's continue. Tell me what you get next.
X is equal to 2.537 times 10 to the negative 4th.
Now that we have an answer, we should put in units. What are the units on that number?
Molar.
Now what?
Now we can fill in the x's.
Okay, so what number goes here?
2.537 times 10 to the negative 4th.
Okay, good. You could fill in all the other x's in your table, but that's not really necessary. Let's just try to answer the question. What was the question asking us for?
What is the pH? So this is the concentration of the protons. So get the negative log of that number of x. pH is equal to 3.595.
All right, that's went round to 3.596. Okay, does that match our prediction?
Yes.
So now what?
Now we found the pH.
Okay, so what's the answer?
3.596.
Okay. All right, so that's another type of problem that we've learned how to do. Each of these acid-base problems, unfortunately, is a little different than the other ones. Okay, so let's review. What type of problem did we just learn how to do from the handout?
Weak acids.
Yeah. Now we've learned how to do a weak acid problem. You should notice this was quite different than how we did the strong acid problems. So oftentimes students confuse weak acid and strong acid problems. So notice the handout doesn't tell you how to do the problems. It would take too much space to show how to do the problems. The handout is just summarizing all the different types of problems. By the way, did you have a chance to watch any of these videos? Or did you watch any of the video series I sent you?
I didn't know.
Okay, that's okay. So that just means we have to go through that together now. All right, but like I was saying, you can the handout does show which videos to look at for each of these various types of problems. Okay, so we've learned how to do weak acids. So first of all, how did we know this was a weak acid? Well, for one thing, they gave us the Ka. Remember, if they tell you the Ka, it must be a weak acid. How was this different than doing a strong acid? So there were a couple of big differences. The first big difference is that we had to use an X in our before change after table. Remember that when we work with strong acids and bases, we don't need any X's. That causes a lot of confusion, so I'll repeat that. When you work with strong acids and bases, you don't need any X's because you know the changes. But when you work with weak acids, then you have to use X in the table. So the table turned out to be more complicated. Then the next difference is that we had to use this Ka equation. We don't need the Ka equation for strong acids and strong bases. We only need the Ka equation for weak acids. Remember, only weak acids have Kas. So I don't know if you remember how to write these from chemistry. Remember, you put the products on the top and the starting material on the bottom for weak acids. Okay. And then we had to do an approximation. Remember, the approximation is, even though the actual amount afterwards is 3.7 times 10 to the negative 3 minus x, that would make the equation too complicated. It would make this denominator too complicated. We'd have to use the quadratic formula. So you approximated by just saying there was just 3.7 times 10 to the negative 3 afterwards. So that's an important approximation that your instructor would always expect you to use. How did you know that X stood for the H plus concentration? Well, you can see that from the table. From the table, we can see that X stands for H plus. Notice it's not really necessary to go through and plug in for all the X's. You don't need to plug in for every single X in the table, 2.537 times 10 to the negative 4. All we care about is this, the H plus concentration. So we can just focus on this, the H plus concentration. Okay, so that type of problem is more difficult than the ones that we did before. Is that making any sense? Do you have that in your notes?
Yes.
Okay.
I just missed the part. You said that only Ka is just for weak acids, not weak bases, right?
I didn't see any questions about weak bases in the materials you sent me. So sometimes Ka is could be involved for a weak base, but hopefully that's something we don't need to cover. All the problems in the lecture and in the problem set, they were all about weak acids, not weak bases. So Ka could come up for weak bases, but hopefully that won't come up in your course. If that answers the question. So weak bases are a whole different case. Weak bases, you could see a Ka, but I don't think you're going to be tested on that. Okay. All right. So for our purposes, we can just say we've gone over strong acids, strong bases, and weak acids. That's enough. All right. Otherwise, does this make sense?
Yes.
All right. The important thing is don't confuse how we do weak acids with how we do strong acids. They're two totally different methods, or not totally different, but somewhat different. Okay, copy this down, and then let's try this on your screen.
How can a proton be aqueous?
Do you remember what aqueous means?
Soluble in water.
Not quite. It means dissolved in water. Does that answer your question? There isn't any reason why we couldn't dissolve. So actually, protons dissolve in water quite well because they're polar and charged. So aqueous doesn't, yeah, so it's important to keep in mind aqueous just means that it's dissolved in the water. Before we continue with the math, let's get a prediction. What could you predict about your answer?
The pH is going to be below 7.
Because we've added acid. Okay, good. Let's continue.
I kind of remember this from second semester Gen Chem.
Yes, this is really just a review of general chemistry. Now, I'm not sure where you got that 1.74 times 10 to the negative fifth.
Oh, was it 8.7 times 10 to the negative second?
Well, you tell me. How do you know what to write there?
Is it? I don't know if I wrote everything correct. You had, right? Like the two numbers are 8.7 times 10 to the negative second.
Right.
And oh, never mind.
I think you wrote it down correctly.
Yeah, I just didn't see the way I wrote it. Sorry. Okay.
So how do you know that the 1.7 is the wrong thing to write there?
Because that's the Ka.
Yeah, so we don't want to confuse the numbers with each other. Okay.
Do I have to? You want me to write out minus x?
You can just explain what you're doing. Why would you leave out the minus x?
Because it's so insignificant.
Yes, as an approximation. That's fine. That 1.4 times 10 to the negative 5, where did you get that from?
It's the Ka.
Okay, you must have miscopied that. So that should be 1.74. You should fix that in your notes so that you have that correctly.
I have a very bad calculator on my phone, so it's taking me a little bit to write everything out.
Okay.
Is it 0.001?
Yes. Yep.
Okay.
Is that what you were getting before? Is that what you were getting before?
Yeah.
What, is there any reason why you were suspicious of that?
It's just I didn't see the numbers afterwards until I just flipped the phone sideways.
Okay. All right.
Okay, so.
Hi, you cut out. Let's try again.
2.909.
Ah, okay. So now what?
The pH is 2.909.
Okay, good. You have to know when you're done. So we can write that down as our answer. Did that match our prediction?
Yes.
Okay, good. So let's stay on your screen for a moment. One thing I wanted to do here is it's always the best habit to write the general equation before you start plugging in. That way we have the best understanding. So before writing your x times x divided by 8.7 times 10 to the negative 2 equals 1.74 times 10 to the negative 5, above that, let's write the general mathematical equation for acid ionization here. What would be the general equation that we would write down first before plugging in stuff from the table? And you should actually scroll down a little so you can see the chemical equation, because the mathematical equation is based on the chemical equation. Good. Okay, good. It's always best to write the general equation before we start plugging in. That helps us to have better understanding for what we're doing. So that's what I would call the mathematical equation here for acid ionization, based on the chemical equation. Good. Okay, so what type of problem did we just do from the handout?
A weak acid.
That's right. So remember, don't confuse that with how you do strong acid problems. For strong acids, you wouldn't need any X's, and you wouldn't have a Ka. So those are different types of problems. It's important not to confuse those. Good. Okay, so that's good. So to continue, does this indicate a relatively strong or a relatively weak acid?
Relatively weak acid.
Any particular reason you said that?
Because any Ka represents weak acids.
Oh, okay. Yeah. Well, any Ka represents an acid that's weak in the absolute sense. If there's a Ka, it's a weak acid in the absolute sense. But remember here I was asking you relatively. What I mean is if one Ka is bigger than the other, if one acid has a bigger Ka than another, does that mean that it's relatively stronger or relatively weaker? Maybe I should make it clear, bigger. If one has a, yeah. That doesn't mean it's strong in the absolute sense, but it's relatively stronger than something with a smaller Ka. All right, now the next concept we have to go over is very important for the course. It's the pKa. You and I haven't talked about that yet, but how do you think you would calculate a pKa?
Get the negative log of Ka.
That's right. That should be easy because P always means take the negative log. Good. So remember we have two different levels that we've talked about. We've got the concentration level and we've got the P level. Ka is at the concentration level. Ka is used at the concentration level. pKa is used at the P level. So those are two different levels. So here we have the pKa. That's the negative log of the Ka. Good. So if one acid has a bigger pKa than another, does that mean it's a relatively stronger acid or a relatively weaker acid?
A relatively weaker acid.
How did you figure that out?
Because negative log of the number, so it's smaller.
Okay, good. So the key thing is, when x gets bigger, what happens to p of x?
Gets smaller.
We talked about that previously. So when pKa gets bigger, what happens to Ka?
Gets smaller.
Okay. Now, this causes students lots of confusion. Do you see how students could get confused? They get confused between the Ka and the pKa. They don't realize they move in opposite directions. They learn that a big pKa means that you're a weak acid, and then they think that means a big Ka means you're a weaker acid. But it doesn't work that way. And also people get confused because they confuse the thinking in terms of relative and thinking in terms of absolute. In absolute terms, anything with a pKa would be a weak acid. In absolute terms, anything with a pKa is a weak acid. But in relative terms, a bigger pKa means a relatively weaker acid. So these are some very important ideas for the course, not to get confused with each other. Okay. So one thing we should do here then is I find that students often confuse pH and pKa. What's the difference between the pH and the pKa? So let me try to explain that. The word acidic actually has two different meanings. When you say something's acidic, you could be saying your solution is acidic. You could be talking about an acidic solution, or you could be talking about an acidic molecule. What's an acidic solution? An acidic solution is a solution with more protons than hydroxides. An acidic solution is a solution with more protons than hydroxides. What's the definition of an acidic molecule?
Solution, molecule that donates protons.
Yeah, an acidic molecule is a molecule that wants to donate protons. The more it wants to donate protons, the more acidic it is. So you see, these are just two different meanings of acidic. If you say the solution is acidic, you mean it has more protons than hydroxides. If you say a molecule is acidic, you're saying it wants to donate protons. So you have to keep in mind the word acidic has two different meanings. What do you think we use? So what do you think this measures? Does H+, does this measure how acidic the solution is, or does it measure how acidic the molecule is?
How acidic the solution is?
Because it tells you how many protons are in the solution. How about pH? Does that measure how acidic the solution is or how acidic the molecule is?
How acidic the molecule is.
Any particular reason why you said that?
For the pH is molecule because it's negative. No, because it's the solution because it's the negative log of the concentration. It's measured by the concentration of hydrogen or concentration of protons.
Okay, so your second thoughts were better there. Your second thoughts were good. You reminded yourself that pH is the negative log of the H+. Well, we just said that H+ measures how acidic the solution is. So pH also measures in a different way how acidic the solution is. So the acidity of the solution is measured by H+ or by pH. Remember, there's two different levels. At the concentration level, the acidity of the solution is measured by H+. At the P level, the acidity of the solution is measured by pH. There are two different levels for measuring the same thing. How about Ka? Does Ka measure the acidity of a solution or the acidity of a molecule?
Molecule.
Yeah. I don't know if I quite explained this carefully, but every acidic molecule has a different Ka. For example, we saw here that acetic acid has a Ka of 1.74 times 10 to the negative fifth. But other acids would have different Kas. Every acid has a different Ka. That measures the acidity of the molecule, not the acidity of the solution. So the acidity of a molecule is measured by the Ka. How about pKa? Would that measure the acidity of the molecule or the acidity of the solution?
Solution. Molecule, sorry.
How do you know it measures the molecule?
Because it uses the value, the negative log of, the inverse log of Ka.
Right. So it's measured by Ka or by pKa. These are very important ideas to get comfortable with because they'll come up in the whole course. So this is a very important table we're building here to try to not get confused between these different ideas. So how do students get confused? First of all, they confuse the levels. So notice at the concentration level, we use Ka and H+. At the P level, we use pKa and pH. So you always have to ask what level you're working at, the concentration level or the P level. Ka is at the concentration level. Also, though, the biggest confusion is that students don't realize that there's a difference between saying the solution is acidic and saying a molecule is acidic. So they have trouble distinguishing pH and pKa. So let's see if that's making sense. What's the difference between pH and pKa? Does the pH measure the same thing as the pKa?
pH measures the concentration of protons, and pKa measures the Ka of the molecule.
So it measures the acidity of the molecule. And then what does pH measure? The acidity of the solution. So the pH is related to the proton concentration, which tells you how acidic the solution is. pKa is related to Ka, which tells you how acidic the molecule is. So those are two different things. What does it mean if we have... So what does it mean if you have a big H+? How would you interpret that in words?
A big H means it's more acidic.
Who's acidic?
It's a strong acid.
Who's it?
The solution.
Now, we don't say that only molecules can be strong or weak acids. But yeah, so is this measuring, so try one more time. What does the big H+ mean?
Big H+ means an acidic solution.
That's what I was going for. Yes, it means an acidic solution. What does this mean in words?
Big pH means an acidic solution.
So you're saying these two things mean the same thing?
Big pH means a basic solution.
All right, so it looks like we were mistaken there at the start. Does H+ move in the same or the opposite direction as pH?
Opposite.
So we don't want to confuse those. Okay. What does this mean?
A big Ka means an acidic molecule.
Yeah, a relatively acidic molecule. Remember, it would still be weak in the absolute sense, because otherwise it wouldn't have a Ka. But relatively, it means it's a relatively... What did you say? Relatively what?
A relatively acidic molecule.
Yeah, a relatively acidic molecule. A relatively strong acid. What does this mean?
A big pKa means a relatively basic molecule.
Put it in terms of acidity. When we're using pKa, we probably wouldn't refer to it as a base. It's still an acid.
A relatively weak acid.
That's right. So this is a little tricky. Okay, so notice the big thing is don't confuse pH and pKa. The most common mistake people make is confusing pH and pKa. So these are very important tables to have in your notes and to kind of study and meditate on, so we're not getting those things confused with each other. The pH tells you how acidic the solution is. The pKa tells you how acidic the acid is. Those are two different things. So this table is important. This table here is important. All right, do you have that down?
Yes.
Okay, so what types of problems have we learned how to do so far? We've learned how to do the first 4 problems here. We know how to find the pH in pure water. We know how to find the pH in a strong acid. We know how to find the pH in a strong base. We know how to find the pH in a weak acid. Remember, you should carefully review those because they're all done slightly differently. Remember, the only one where you need an X is the weak acid. These are all slightly different, so it's important to review your notes for these. This one you might cross out. I don't think your class is covering this. So I don't think we need to cover the weak base case, hopefully. This case we really have to cover. This is very important for the course. So before we can move on, we need to cover this. Or you could watch the videos for it. So if you want, you can watch these videos for this case. But we can't move on to the next material until we've done this. This involves the Henderson-Hasselbach equation. That's very important for the course. So we have to cover that before we can move on. But if you watch these videos, then that would definitely save us some time. And after we do that, we should probably move on to the next chapter on amino acids. So you had some review problems that actually dealt with these. Some of these cases were in the review problems, but these weren't in the lecture notes. So I think we'll hope that these won't be on the test, and we'll just do this one more case and then move on to the amino acid material, so we don't fall too far behind. So like I was saying, you might want to cross off the weak base part because I don't think your class is covering that. Hopefully. And you might want to watch the videos for this one, weak conjugate acid and weak conjugate base. That's the Henderson-Hasselbach equation. That's very important. Here's the videos for that. And then these cases down here, there were some problems in the practice problems that dealt with these. You can watch the videos if you want, but I don't think we'll have time to get into that. We want to keep moving on. Remember, the key thing is you have to keep the different cases separate so you don't confuse them. So in our previous tutoring session, we went over how to deal with pure water and a strong acid. So you should review that. And then in today's session, we went over how to deal with a strong base. Here was the example with a strong base, and then we did a couple examples with weak acids. Okay, so that's our time for today. All of the examples that we did today were similar to the examples in the lecture notes, so I think there's a good chance they would be tested.